I'm going to talk on pricing and have a few remarks about bid and demand, but it's not going to be a focus of my talk. But I think bid and demand is a really important part of future market designs, and we're just getting started on that issue. It looks like the Europeans are way ahead of us, but I think it is absolutely crucial to making these markets work and to getting prices right. Okay, here's the outline of my talk. First of all, I'm going to talk a little bit about economic equilibria and auction models, convex markets and the role of prices in convex markets, but then we will find out that convex markets don't help us very much, and look at the idea of mechanism design. In particular, repeated two-sided auction markets, which is what the electricity markets are. And the electricity markets, although not unique, have scale economies generated by binary variables, and essentially we lose most of the properties of convex markets when we introduce these scale economies. I'm going to talk a little bit about the marginal cost controversy and how it fits into the pricing methodology that I'm going to talk about today, that includes average incremental cost and Ramsey plateau prices. I'll give you a couple small examples to motivate things, and then look at some results from the MISO markets in the United States. In the US, probably different from Europe, prices and procedures in ISO markets are regulated under the just and reasonable standard, which has been handed down from centuries of debate from the ancient Greeks through the Roman Church. And Thomas Aquinas wrote considerably on the issue of a just price. In the US, up until the 90s, a just price was set by what is called cost of service regulation. In the 90s, we decided that that may not be the best way to continue regulation. And so we took a shot at competition and open access, both in natural gas and in electricity. And most of the 20th century, at least my time, has been spent on standing up and improving ISO markets. If you look back to about the middle of the last century, you find two dominant theories of equilibrium, one Arrow-Debreu, but this equilibrium requires strong assumptions, effectively convex markets, and the Nash equilibrium, which requires the knowledge of all the behavior of the market participants, but without cooperation. These two approaches don't give us much help in dealing with non-convex markets. But before we get to non-convex markets, a little bit of a review of convex markets. In strictly convex markets, the law of one price holds. That is, the prices that you get out of the dual formulation are unique, and the global optimal solution is the only solution. But if you relax the strict assumption, the convex market prices are not unique, and what we're showing here is that the prices will, any price in this tunnel will clear the market. All right, so let's move on to mechanism design. Mechanism design, there are four properties that are considered important. Economic efficiency. Oh, by the way, if I forgot to say, if you have questions, I'm willing to take them during the talk, although I probably won't be paying attention, and hopefully the moderator could interrupt me if there's a question. The mechanism design has four important properties: economic efficiency, individual rationality, a balanced budget, which essentially means that you have to have enough money from the buyers to compensate the sellers, and truthfulness. But we have a theorem that says there's no mechanism that exists that has all four qualities. I would just remind the audience that incentives in this system are not always positive, and that seems to be a theme that runs through a lot of these pricing issues. Although the US ISO markets use penalties for various types of misbehavior. Now, the repeated two-sided auction, which is essentially what we're getting to in electricity, is a mechanism for clearing markets with multiple buyers and sellers. And in these markets, the prices need to have at least two important functions. One is that they clear the market, and the second is they signal future decisions. And to do either one of these, the prices have to be transparent. Why auctions? Well, the simplest answer is that they lower transactions costs. They don't require detailed negotiations. Walras thought that they were the best way to introduce efficiency in these markets. No one loses money. And the interesting thing is that Walras market clearing, or tâtonnement, is considered by some now to be the solution algorithms to these more complicated markets instead of an iterative pricing regime. And each one of these auctions usually gets designed with unique participation models and rules. Now, the marginal cost controversy started somewhere around the middle of the last century. And what we quickly understood is that marginal cost prices in markets with declining average cost may result in negative prices, violating individual rationality, and or require a make-whole payment. Hoteling thought that the government should pick up this make-whole payment. Coase later on said, no, I don't think so. Buyers should pay the full cost of the sellers. And over time, it looks like Coase won because the government isn't picking up the make-whole payment in the US. The pricing has to be Ramsey-Boiteau in this case, which is some of the products are priced at above marginal cost, and these prices are paid by the buyers with higher values. I'll skip over the definitions because I'll go through them as I go through the presentation. First of all, I'd like to say that what I'm going to talk about is average incremental cost pricing. And does it pass the bilateral negotiation test? Even though we do have auction markets. And the answer is sure, and I won't go through all the details, but AIC passes this test and most other pricing mechanisms don't. Now, differential pricing is a fact of life, as are scale economies. And you need to look at airfares, hotel rentals, commercial office buildings to see that differential pricing exists and is natural, and most people accept it. Although you'll find an interesting debate about what the price of an equivalent airline seat should be. And in the U.S., we have, and in the EU, you have economies of scale in the electricity markets, and that creates a pricing problem. The primary function, at least in my opinion, of the auction is to create a Pareto efficient set of dispatches. The second question is who gets the market surplus created by the auction? Without regulation, it would depend on whether or not these markets are competitive, oligopolistic, or monopoly, and that would essentially decide who gets the market surplus. But an important part of these markets is to signal entry, although one of the important things we have to understand is these are not deregulated markets. They are still regulated under the Federal Power Act and the Just and Reasonable Standard. Generator, and I've added here consumption, because if you look at industrial consumption, it's not a whole lot different from generation. It has fixed operating costs and variable marginal costs, minimum and maximum operating levels, minimum run times and downtimes, and ramp rates at the speed at which you can change your operations. In the US, we have multiple periods, a transmission distribution network, and I've added here topology optimization. One of my catchphrases at ARPA-E is the optimal power flow problem is not optimal unless you have the optimal transmission network. This is up until recently, this was a taboo in most of the optimization circles. And recently in the US, we have Order 2222, which is essentially going to open up the bid-in demand market in the US. We also in these markets have what we call offer mitigation and penalties for misbehavior, and I won't go into the details of what that means. And those two parts of the market incent truthful bidding, and I guess you could put incent in quotes. Now, I like to look at ISO markets as a knapsack problem in time and space, where you're looking for different shapes and boxes to stuff into a specific area. And then once you do that, you actually open the boxes, and then you have to solve another problem, and that is to allocate what's in the boxes to consumers. In the old days, the approach was to do a Lagrangian commitment, which usually created an infeasibility. And then you had to find a redispatch to find a feasible but usually non-optimal solution. We recently switched, and all of the ISOs now do this, they use a mixed integer programming approach, and then they iterate to solve for AC feasibility, which turns out to be a much better and more efficient market approach. Now, to move to pricing, if you had a convex market, the convex problem has a dual, no duality gap, and the prices basically clear the market. If the market is a mixed integer program, there is no dual problem comparable to the one you get in the convex market. And so what you can do, and what Ben and I did 15 or 20 years ago, I can't remember, is we invented dual, fix the binaries, solve the resulting linear program, and the LMPs do not recover all avoidable fixed costs, and you need make-whole payments to go to make the generators whole. The second one, which had bothered me for quite some time, is the average incremental cost approach, which is to say we relax the binaries, we tighten the formulation, then solve a linear program. And it turns out that both empirically and theoretically, it allocates all the costs to all the fixed costs are allocated through the dual variables, and you have market efficiency. But you need if there's a bid and demand side, you need Ramsey-Plateau pricing. There are no side payments, and prices are entry signals, unlike the prices from the first pricing methodology. All right, let me give you an example. Suppose we have a generator with $2,000 startup costs, $20 marginal cost, and a maximum of 100. This plot here, the green line, decreasing average costs, is the representation of generation A. If you have a vertical demand curve, those decreasing costs intersect the vertical demand curve at a price of 48.50. 48.50 clears the market on the generation side, and since a vertical demand curve says that the consumers are willing to pay anything for the electricity, it clears the supply side, or the demand side. The LMP, as you can see down here, is not an entry signal, and it doesn't clear the market. Now, if you put in a demand curve with a slope, which is infinitely rational because you don't have anybody who's willing to pay an infinite amount of money for electricity, things change. You cross the generator's cost curve crosses the demand curve here and at the LMP. And if you don't use Ramsey-Boiteau pricing, you don't get market efficiency, because this would be the price up here if there wasn't this differential pricing. And so the LIP, if you go all the way to 90 megawatts, is $42. Now, there are various and sundry ways to approach the Ramsey-Boiteau pricing. I won't go into the first two. Needless to say, they theoretically end up with the optimal surplus. But if you don't use Ramsey-Boiteau pricing, you decrease the total market surplus, which is inefficient. Now, is it an entry signal? Well, here I've lowered the cost of entry for generator, or startup for generator B, and you can see that the criterion is that there's a lower average incremental cost at 90 megawatts, and that's essentially would say that generator B displaces generator A. Again, the LMP does not work for this. When I made this up and looked at it after I'd made it up, it looks really complicated, but this is the standard decreasing and then increasing economies of scale, and then diseconomies of scale. If the demand curve intersects on this left-hand side, you get the picture that I just presented. If it intersects on the right-hand side of the minimum, you get short-run profits, which are the recovery of investment costs. And what we often don't realize is that this is a bad, what I just put up there is a bad depiction of scale economies and diseconomies of scale, because almost all of our generators have a maximum output, which essentially represents the supply curve gets represented by this vertical portion here. And if the demand curve intersects the vertical portion, we call that an infra-incremental generator, and the demand side here sets the market price. Now, moving on to MISO, my co-author here generated these examples where she calculated the LMP profit and the average incremental cost profit. And you can see here that they're not a whole lot different at this scale. When we get down to the last units, these are ordered, we see some LMP profits going negative. If we zoom in on this, what we see is there are 9 incremental generators. Incremental generators are defined as having 0 profit at the locational incremental prices. And these generators, interestingly enough, cover all periods of the system. There's a point here, which is basically due to the fact that we sorted on AIC, on the LMP rather than the AIC cost. Once we go beyond the incremental generators, we have incremental generators, excuse me, they all make profits. On average, the AIC is about 10%, AIC profit is about 10% higher than the LMP profit. Now, some of the AIC minus the LMP profit is negative, and we couldn't figure out exactly why that, and we developed a hypothesis it could be the transmission constraints. And so if you remove the transmission constraints, lo and behold, all the negative profits from the difference disappear. And this is not surprising because the transmission network and the physical equations of how the stuff moves around in the network can create very strange effects. Now, just to summarize, AIC prices are transparent, clear the market. They're crowdsourced, not administrative. They have no administrative demand curve. The prices, that's to say, if you have bid and demand, price signals for incremental and marginal entry into this market. No uplift, there's no make-whole payment, no opportunity cost payment. All the scale economies are incremental. Then the LIPs are LMPs. And we have Ramsey-Plateau pricing for the demand side. Also, there are better incentives for market participants. There are higher profits for incremental generators, and usually almost all of your renewables are incremental. And there are lower capacity market prices because there are higher energy market prices. The incremental generators have zero profits and are the entry for the target for new entry. The one thing this doesn't do is it doesn't have positive incentives for self-scheduling. It has negative incentives. It says essentially that we don't pay people to rob banks. There's not enough money to do that. And generally, we punish people when they rob a bank and we catch them. Also, interestingly enough, in multiple periods, the costs are allocated to the period that generated the highest need for this the generator. And the flow gate inframarginal price, which is similar to the flow gate incremental price, which is similar to the flow gate marginal price, is a signal for possible efficient transmission, even though the flow gate marginal price may be zero. Offline resources are not part of the optimal dispatch due to their operating costs or constraints. There's no compelling reason, and this is my opinion, for paying them anything. And if you do, they'll cause revenue inadequacy. Quick statement about capacity markets. They have been a problem because of shaky assumptions. What's the value of load?
Thomas.
Yes?
I actually came across another figure somewhere, I don't remember, where they talk about, yeah, here we are representing 100% load, but momentary overloads with the respective number of minutes or hours we can go for that kind of overload.
Is that a question for me or what?
Right.
I'm not sure what the question was.
Maybe we can defer this to the discussion part.
Okay, well, let me just keep going. So the capacity market was instituted to recover investment, often called the missing money problem. And capacity market prices, in my opinion, again, are a bellwether of unrecovered investment costs in the energy market. And you know, they may be a risk premium on top of normal prices, and they're there to recover the missing money in the energy market design. With average incremental cost pricing and bid and demand, the capacity market price is not needed to recover investment. And probably has a clearing price near zero where risk premium and no administrative demand curve is needed, which I consider a positive. And that concludes my talk. There are some papers if you're interested in the math or additional examples or anything else. I have some papers that I can send you, and here's my email address.
For making this meeting possible. I also want to thank my fellow panelists. So Dick and Frank Wolak have long been colleagues of mine and have taught me an awful lot about markets and market monitoring. Dick grabbed me by my collar in 1995 when I first moved to Johns Hopkins and said, "We have some interesting problems here. You should work with us." And I did. We had a lot of fun and made a number of contributions, which Dick mentioned. And then Frank Wolak was the chair of the California ISO Market Surveillance Committee when I joined in 2001, and taught me an awful lot about how markets actually work. And you're really going to enjoy his presentation as well later on. I also want to congratulate the organizers for the incredibly comprehensive and visionary white paper that you've produced. And if you haven't read it, I definitely recommend it to you. You'll learn a lot more from it than you will from my talk, that's for sure. I'm going to ask that questions be held into the end because we have about 100 participants, and I think that will be more efficient. And a quick question, will the slides be posted? I think the answer, Vanessa, was that we'll be doing that so you can get access to my slides and the references that way. Okay, so in addition to thanking Frank and Dick and Martin and everybody else, I want to thank my colleagues on the Grid Management Laboratory Consortium for their suggestions and for funding. And as usual, the blame for any opinions and mistakes is mine, and my opinions do not represent the opinions of the California ISO or anybody else for that matter who thinks clearly about these subjects. Okay, so what I'll do is talk about the general goals that motivate the U.S. approach to markets, in particular, why is it built around LMP? I'll talk about whether the goals and principles are altered by the new technologies that are coming on the horizon, variable renewable storage, DERs. I will then talk about some general approaches, strategies for changing the markets to accommodate these. And in particular, I'll focus on the California Independent System Operators incremental approach, and I'll mention just some of its initiatives at this point to give you a sense of how complicated it can be to implement this in practice. So here are some goals and principles. So the general goals are efficiency, maximizing net benefits, respecting the policy and other constraints, and also having a process that builds social cohesion and consent. And the principles in terms of pursuing these goals include making sure that the designs really are implementable and have widely agreed upon benefits, and that we do pursue social goals such as environmental justice at costs that are equitable and reasonable, whatever that may mean. The principles for efficiency include some of the following. Prices need to reflect system benefits and costs and are such that the incentives for private profit align with social benefits and costs. Incentives really do matter. Furthermore, we need time consistency from minutes to decades. The markets need to flange up. As Dick emphasized, we do need to recover lumpy costs. We do have scale economies, for example, in networks, without distorting things too much. And finally, this is crucial. Every time you think you understand what's going on with the industry, it changes. That's why it's so much fun. We have to manage uncertainty. To have supporting prices, people need to bid truthfully and not manipulate the market. That is, the bids need to reflect people's real benefits and constraints. Second, we have to clear bids considering the full network, getting all externalities included. And finally, we need, for dynamic efficiency, a level playing field. So if somebody invents that better mousetrap, the world can truly beat a path to their door. And we need to focus on technologies that meet our ultimate objectives of environmental improvement, reliability, and energy. So we try not to pick winners. And then there are various things we need to consider in efficiently managing uncertainty. And given what happened in Texas and in Puerto Rico in the last few years, extreme risks are really important. Societal costs of hurricanes and shutting down the grid need to be recognized, and we need policies that deal with those. So, implying these principles in U.S. markets, there's been largely a consensus that we need spot markets that have multiple settlements, day ahead and balancing, that co-optimize not only energy, but reliability services and use of transmission all at the same time. And we need from the market participants detailed bids that reflect their internal constraints and costs. Now, folks question these principles, and they may change in the future, but this is what we do right now. And this is very much a contrast to, for example, the European system with Euphemia, where we don't get detailed bids that have, for example, constraints for multi-stage generators, combined cycle, state of charge, etc. We clear the market with detailed network models. This is another distinction from the European model, which has zonal pricing, emphasizes a zonal approach, although that is changing. And finally, the settlements for energy are using dynamic prices that are locational. There are a lot of exceptions about this for demand in the name of protecting consumers. We can talk more about that later. Capacity markets are an important element in many markets. I think that they are in general needed to provide political assurance, both belts and suspenders. Although the presence of capacity markets might not have made much of a difference in Texas in February, I think that they can help. And anyway, at the moment, they are a pillar of U.S. markets. And finally, we do ex-ante market power mitigation. We take a look at bids, and if they're not cost-based and could affect prices, we mitigate them before we clear the market. This is definitely a contrast to the European approach. So the linchpin of all this is locational marginal pricing. And locational marginal pricing is basically calculates a set of prices that you clear supply and demand in most cases that represent the marginal cost and marginal benefit at each location in the network at each point in time. And it's most easily calculated as a dual variable to an optimal power flow. Like any optimization problem, you have an objective function that you're maximizing subject to a set of constraints that tell you what combinations the decision variables are feasible. And the LMPs are the shadow prices, Lagrangians, to the real power energy balances at each bus. So if you don't have degeneracy in the primal solution, if you freeze the 0, 1 variables, you can calculate dual variables that are the change in the optimal objective function value with respect to load. And you can decompose those into some of three things. First of all, the cost of supplying energy at some system hub. such as Moss Landing in California, or maybe an average of costs across various buses, plus the cost of getting it from the hub to the particular location, which includes the cost of losses, marginal losses, which might be positive or negative, and congestion, which might be positive or negative. For linear power flow models, congestion costs are a weighted sum of the marginal cost for transmission constraints across the system. And Bill Hogan of Harvard has done the most to champion a public understanding of these relationships. However, he is a disciple of St. Fred Schweppe of MIT, who in the 1970s first envisioned calculating these LMPs and using them to affect decisions. Interestingly, the decisions he was focused on was on the demand side. An incredible irony, given what Dick said and what I'll say, that we have half a market that most of the demand side of the market is not really engaged, has no idea what the price is at any moment, and is not varying its consumption based on system conditions. Fred was focused on that. Send people prices and shape the load to accommodate system and other constraints, and optimally balancing the value to consumers versus the cost of generation. So it's a supreme irony that one of the big surprises with that he would see today is somehow we're focused mainly on the supply side. Now, eventually, after a few years, he got some smart students, including Roger Bone and Mike Karamanis and others, to flesh this out and say we could include generators also. And I totally recommend their book, their 1986 book on this topic. And those LMPs have become part of what might be called the standard market design. And under certain assumptions, St. Fred's marginal costs, these solutions, the OPF, are also equivalent to the prices from a competitive market. We get efficient dispatch, and we even get efficient long-run investment in generation and, strangely, even transmission under a bunch of assumptions. So LMPs support the optimal solution, at least in theory. Now, in fact, there are a lot of things that get in the way of that. Dick has talked about that. And so an awful lot of market design is figuring out what those market failures are and how we can correct for them. But the basic framework, using LMPs to support at least short-run decisions and be an input to long-run decisions, remains. So what I mean by supporting prices is that the LMPs are such that the socially optimal schedule and generation capacity, resource capacity, is also profit maximizing. And maximizing the area under the demand curve minus the area above the supply curve gives you the market clearing solution, and these prices are also will also result in the profit maximizing decisions. The amount of capacity, the width of these steps, and then how they're operated. Now, there are all these assumptions we could pick at. We assume that there's no market power, and of course, as Frank will tell you, in 2000, in 1999, 2000 California, we got a rude wake-up about that. We have largely but not completely controlled market power. We assume that prices are not sticky. There's perfect information. We assume convexity. Dick talked a lot about that. And finally assume that you can compute the solution, which is actually not really true. You can get close to the optimal solution, but there are some very interesting issues that Dick and I have worried about with the help of incredible students such as Brent Eldridge to figure out what the implications are of stopping the optimization short of full optimization. So there are a lot of remaining challenges to LMP. Some of them are still dealing with these assumptions, such as no lumpy costs. One of them is, of course, the fact that we only have half a market. It's like going to the grocery store and picking things off the shelf, steak or what have you, without having any idea what the price is. Less than 1/20th of residences are in time-varying rates. We have spent billions of dollars on smart meters, so-called smart meters, but we don't use them for communicating this information. And we have huge wholesale retail price discrepancies where my snotty-nosed kid in Southern California pays 40 cents a kilowatt hour. So, of course, he puts 30 kW on his roof. That's the right thing he has to do with his family. But meanwhile, wholesale prices that are 40 cents are 3 to 5 cents and are often negative. And so there's a huge cost shift from my snotty-nosed kid to people who live in apartments. There are a lot of missing constraints. We are constrained in terms of geography and also in terms of time. We're missing a lot of constraints, and so we get distorted prices as a result. And so a lot of about market enhancements is increasing the time horizon and increasing geographic scope. Non-convex costs, as Dick emphasized, mess with supporting prices. And on average, these resulting uplifts to cover for the losses of people we want in the market are something on the order of 5% of total costs. They're significant, but they're not overwhelming. These markets are solved assuming certainty and often for large time intervals, day ahead for an hour. So that suppresses price volatility, which means we undervalue options and flexibility. And finally, investment, to everybody's surprise, in the beginning, is driven mainly by policy and not by spot prices. We thought that the main benefit of LMPs would be to shove risks on investors so they make more rational decisions. And generally, we're not building big nukes anymore. There is more rationality, but we haven't got the efficiencies investment, as many efficiencies as I thought we would get. We've gotten more efficiencies in operations, so that's been a surprise. Okay, so how do variable renewables and other new technologies change these principles? Bids reflect internal costs. Internal costs are no longer fuel, but opportunity costs over a long period of time. The full network may be the distribution network if we're talking about DERs. Level playing fields for entry. We have even more policy interference in terms of government decisions about shutting down nukes in Sweden, Belgium, and Germany, and about which technologies should be favored for new technologies. So the level playing field is becoming less level all the time. We have new risks in the markets without hedges for those risks. We need to figure out how to allocate those risks to those who can do something about them. And finally, we have even more social goals. Once you start putting panels on people's roofs, cost allocation becomes more important, as I mentioned with my snotty-nosed kid, and we need to figure out how to pursue social goals of environmental and economic justice. At the same time, we want people to be able to control their energy decisions. So how will high VRE penetration affect LMPs? Does it completely change things and we need to reform the markets? The naive view is that prices will be bipolar. They'll either be zero at the variable cost of wind and solar or at the price cap because there are shortages. And this will make investment unattractive. In reality, price distributions will change, but we'll still see prices at intermediate levels for substantial periods, and they can be guidance for investment. For example, we're going to have base load plants with some fuel costs for a long time, perhaps indefinitely. As Jesse Jenkins' paper points out, we need some base load clean plants to cheaply control carbon. I love the Kopernikus power to X to hydrogen, for example, research thrust. Evolved Energy has argued that those will be economic and will reduce renewable curtailment from projected levels of 1/3 or more to perhaps 5% or less. They're saying we're not going to need near as many batteries as a result, and I commend their studies to you. Scarcity pricing will also be more subtle and will resulting in raising prices gradually under scarcity. And of course, we're going to get demand more into the market. We're going to fix this half market that we have using, for example, building storage, which is a lot cheaper than Elon Musk's batteries, electric vehicles, and other flexible sources. And finally, storage itself will modify those the bang-bang behavior of prices in a zero marginal cost system. For example, storage degradation is hugely important and underappreciated, and that will smooth price fluctuations quite a bit if it's recognized in markets. And finally, with more storage in the system, opportunity costs of energy, of water will rise and fall more smoothly, accounting for uncertain scarcity in the more distant future, and that will also result in intermediate prices. So here's some historical data. You all know the duck curve, which I would rather call an oyster catcher curve. Looks more like an oyster catcher to me. And folks such as Eric have observed that, at least in the past in ISOs, higher VRE levels, lower average prices, increase the frequency of zero energy prices, increase prices for ancillary services. So he foresaw, at least the trend seemed to be a bang-bang future. And so this shows what's happened to prices. The thinner lines are further in the past. The thicker line is 2018. This is the California ISO. And we see that during the belly of the oyster catcher, we have low prices on average, and that we actually can have higher prices in the peak. And if you take some classic studies of the impacts of more renewable penetration, this is a price duration curve. You can see that as you put in more renewables in the system, the fraction of the time of zero prices grows. But that doesn't account for a lot of the things I talked about: storage and demand response, more subtle scarcity, storage degradation. And what we've actually seen in U.S. markets, that even as renewable penetration has grown, the fraction of the time that we get zero prices has not always increased. We'll see what happens in the future as these penetration levels go up. But I think the story is more complicated because of these factors. For example, Bethany Frew has looked carefully at scarcity pricing, operating reserves demand curves, and has found that with operating reserve demand curves, you go from the dotted price duration curves to the solid ones, again resulting in more periods of intermediate prices and less of this bang-bang behavior that people are anticipating. And likewise, Baud Nadarud and Magnus Corpus have looked at the impact of storage on price duration curves. They definitely smooth them out. And very importantly, they have repeated Roger Bones and Stephen Stoff's analyses of optimal entry and exit in a system where they've added storage and VREs, and none of the fundamental conclusions change. All plants recover their costs. They're all optimally sized and operated, and they recommend that you should think twice before redesigning markets. So let's talk about some of the possible redesigns. This is what the California does in terms of taking the LMP market and tweaking it to accommodate the new technologies. Of course, you then accumulate fixes over time that might create a mess like my uncle's tractor, which has a lot of duct tape and baling wire on it. So at some point you may want to completely redesign it. One possibility is adopt ideas from Europe For example, more clearing, a lot more intraday markets or even multi-day markets where people can take positions and then adjust them. Include a realistic network model so you get the LMPs right, but forget about trying to represent the internal details of every resource. It's just too complicated. People can take care of that on their own. This is the Hayekian type of philosophy that a central market cannot correctly guess people's costs. And what you need is be able to allow people to take positions and adjust them to accommodate their internal constraints. The problem is that we can't then do ex-ante market power mitigation because we don't know what the costs really are. Here's another one. Consumers like today's phone contracts where you just pay for a phone and you get free minutes. If it's really a zero marginal cost world, perhaps we should have those sorts of retail contracts. And people are actually implementing this in some places in the US. But as I've argued, short-run costs will not be bang-bang and can be large. And so I doubt that that will be efficient, but we'll see what will happen. Okay, some other possibilities. Some folks have said we need to go back to an integrated resource planning type of paradigm where we have a big Uber model that that optimally builds transmission and generation, etc., according to people's bids. And with these long-term contracts, maybe we'll get more efficient investment that really accomplishes our carbon goals. But it's really unclear how that will work with spot markets. We'll break the link with spot markets. We don't know how to price imbalances. There are counterparty risks. You sign a 10-year contract. What if they don't show up? And then we have these models that people won't agree upon. And then finally, this is a proposal I like by Brattle, have some clean energy forward procurement, just price the carbon attribute. And this really complements existing resource adequacy in spot markets very well. It is cap and trade under another name, and we do need to carefully deal with imbalances if somebody doesn't show up. But I think that is eminently workable. Okay, so my last slide is about what we're doing in California. At any given time, there are like 30 or 40 different initiatives that are in various stages of development. This is just a few of them to give you an idea what's going on. So Little California, with its stay-ahead and real-time market, has extended its real-time market throughout the West, the energy imbalance market, which is incredibly beneficial because of the diversity of solar and wind resources and load. And we also have competition from other market makers. For example, the Southwest Power Pool would like to come in and create a day-ahead market. Whether competing market makers will be a good thing or a bad thing, I'm not sure, and maybe Dick has an opinion on this. Resource adequacy. We learned last August when we set records for the world's highest temperature in Death Valley that the old ways of just adding up derated capacity and comparing it to a reserve margin just doesn't work. We need to give old RA systems a gold watch and modernize them. And that's underway. We need, with storage, we need, as FERC now tells us, to model the internal constraints of storage, in particular the state of charge. Should we use the energy now, or should we hold it for later in the day? So the US trend of having more elaborate resource models is continuing. We're also creating new products. For example, we have a ramp product that actually buys flexibility, and we need to make sure that flexibility is actually deliverable, is not stuck behind some transmission constraint. So we're going to constrain that by the full network. We may create an aggregate system state of charge product to make sure there's enough energy in all the batteries for the evening. And finally, unless and until we get a national carbon trading system, we're going to have to manage wildly inconsistent carbon rules to deal with the distortions in power trade that result from inconsistent carbon pricing. And right now, the border carbon adjustments in California likely render California's AB 32 largely ineffective in affecting decisions elsewhere to deal with the carbon leakage problem. There are more efficient things you can do. So to conclude, LMP has worked out differently than we anticipated, that St. Fred anticipated. It's mainly supply, not demand focused. It's yielded operating savings, but less savings in capital investment. Although killing off nukes, strangling them in the cradle may have been a good idea and in part can be credited to spot prices. I believe that VREs and storage don't pose a fundamental challenge to the basic principles of LMP. Distributed energy resources do present challenges mainly because of retail wholesale price discrepancies, and resistance is much more important than reactance and distribution networks. Are we going to have distribution LMPs? That's a fundamental challenge, and we'll need to work on that. I believe, though, for now, the incremental approach to the California ISO is justified. And finally, I think Brattle's clean energy attribute auctions are the easiest way to efficiently meet carbon targets. We cannot afford to waste money in meeting carbon targets. When we're just reducing carbon by 5%, paying twice as much as we need to is not a problem. But if we need to reduce it by 100%, paying twice as much as we need to will make it infeasible, and you'll see a lot of yellow vests not only in the streets of France. And the clean energy attribute process works well within present capacity in LMP markets. I invite you to visit our website. We have a lot of great sources on future power market design. This is a joint product with Columbia's Center on Global Energy Policy, powermarkets.org, and I'll be glad to take questions at this point, or please email me. Thanks very much again, Martin.
For this invitation, I'm happy that the previous speakers are old friends. I'm not saying that they are old, but we have been in contact, and I think as Ben said, I am, well, my grandfather Ignacio Pérez Arriaga is also disciple of Saint Fred, as he called. So I imagine we are somehow aligned on our research, and I hope also you find it interesting. So as Martin said, I divide the presentation in two main topics. One is a kind of own research on network tariffs, especially in the current context, as we are all aware of decarbonization, digitalization, and decentralization. I think in a way, this presentation, this first part is very much complementary with Ben and also Dick. And in the second part, I'm going to introduce the OneNet project and especially focusing on the market design aspects of the project. Yeah. So just briefly, this is the outline, as I said, the two topics. In the first one, I'm going to explain a bit our initial research and the utility of the future project. And from there, for instance, Dick was part of the academic board. So also we had good inputs from him, and also we are in close collaboration with Ben in our university, as I said, and follow-up research that we have been doing on tariff design. And I will go through then to the OneNet project, an introduction of the project, and again, also an introduction of the market framework. So, the first part of the presentation, as I said, is to give you a bit of introduction of this, one of the chapter of this big study. This was done, this project took place from end of 2016. I was engaged in the whole project and specifically working on one of these, a lot of chapters, but this one in particular. And the main focus is how to design efficient price signals and charges in the context for electricity services in the current context of, as I said before, decarbonization, decentralization, and digitalization. So of course, previous speakers also mentioned the challenge. I'm not going into details, but basically distributed resources are in competition with centralized generators, centralized resources as well, storage units and others. And the best way, as also Ben said, is that we can put all these resources to compete is to create a level playing field. No? That is the main motivation to do that. Indeed, this is, sorry, I'm from Madrid, so I had to, to put it here. But as I said, the best way to create a level playing field is to improve prices and regulated charges for electricity services. So we withdraw, I will talk about high level conclusions from the project. Of course, behind this, there are a lot of papers and you can find in the report the detailed description. But first thing is that we have to ensure that all prices and charges are non-discriminatory and they are technological neutral and symmetrical. That means that what is important is not what is behind a meter or what is the resource behind, what is the impact it has on the system, and finally the profile they can have. So now it's pointless to talk about consumers or generators, but as you know, there are even new words, prosumers and so on. Well, we can say network users that they have a profile. What is important again is that profile at the connection point and the impacts this profile has on the system. So prices and charges should be neutral, independently of what is behind a meter, but looking at what the impacts each of the resources create to the system. So with that in mind, as a main point, we have been discussing here in the previous talk, and it was very good because the previous speaker really went into the details of all this. And I'm showing here very high level representation, but of course in Europe we are, well, in the wholesale zonal, locational, well, even we are, zonal locational marginal prices, and you can go into more special granularity. So that means that we can move further to systems that have a distribution marginal prices, even at distribution level for both reactive and active power. That is the more granular you can go. And usually Ignacio, the project lead, usually said you can, to the extreme, you can go to the toaster. No, and then each of the consumers will have a different price, of course, and there is a trade-off between that, how much you gain going into the connection point or to stay at substation, transformer, or different levels of locational granularity. On the other side, on the temporal aspect, final customers, also as Ben explained before, there is this mismatch between the wholesale price signals and the retail price signals, and also they can mention it. You know, moving from time of use prices to more real-time spot price is the way also to go, and moving forward to this direction. But even though in those scenarios, if we move to very local and granular in times and location, the next step is that enough to recover all the network cost? And the answer is not. There has been papers from Ignacio with other people and also in collaboration from researchers at MIT that has proven that those signals are not enough to recover all the network costs, and then you need an additional price signal. So in here in blue, you have the energy charge that, imagine, it can change. Well, I put it here hourly, but every 15 minutes if you want. And in addition to that, you can have two additional signals, this generation capacity in case there is a, well, in here, for instance, Dick said that it may not be needed. that is under discussion, but always you need an additional charge to recover the network cost. And how is that charge being computed? For that, you need to forecast what are the future needs, what is the future cost, and create charges that are forward-looking and peak coincident. So what is important from the system point of view is not the individual peak, but is the coincidence of all the peaks at different voltage level, and that is quite important. For networks, maybe a specific area you have a peak because there are residential consumers only, and that peak is totally different if you are in an area where you have industrial consumers. Even if the peak of the system is something in between, you may want to send different signals for these different areas depending on the network usage. And so that's why you have here that there are some hours. Here I put from 17 to 19 hours. So in those 3 hours, you can have this peak utilization of the network, and then there is an additional charge which try to represent the future cost of the network. So if consumers can react to that, maybe they can avoid avoid the charge, and by avoiding that charge, maybe there is no need to invest in network assets. That's a bit the reasoning behind all this. Of course, as I said, this is backed with papers and the detailed formulation, etc. But then network charges is not the only thing that, especially the Europeans, we know that we pay in our electricity bills. In addition, there are policy costs, and in Europe here, what is called taxes is all what is in addition to those energy and network costs, and how we pay for this is very relevant, and is relevant in the as you see here, especially for Germany, where you are after I think Denmark, this percentage of the bill is the most is the bigger part. So not only that, not only this policy cost, but also the residual cost. So in the networks, if they are over-dimensioned, imagine that in a certain area, the future network cost, you can still accommodate the coming consumption and injection increases. So in those cases, that network costs are what is called residual. So you have to recover that, but there is no efficient way to price it. And so all this will become a residual. It's a sunk cost that needs to be recovered. So both the residual cost from network and from policy cost they shouldn't distort the marginal price signal for consumption and production. And finally, and then again, this is a clear message for especially in the European context, as the rest, what is called here taxes, that is not only taxes, but levies and other support from renewables in the past and so on. If you put a lot of weight to this green component, maybe for some consumers, for them it's cheaper to disconnect from the network, and then this becomes the death spiral effect, or that people will start in some cases, and this is already, of course, is a minority, but the cost that they don't pay, the rest that still remain connected have to pay. And there is here a whole debate of how, if there is a need for exit charge, so those that disconnect and have a network that has been built to supply them, if they need to pay for that network. And of course, this is not, that's why it's with question mark, it's not as straightforward, and you can find a lot of arguments in favor and against it. But of course, this is a challenge. But the main message is be careful of how much you charge consumers, because there is this risk. And finally, of course, the just transition, we want to make sure that those people with low income, they are not affected with energy policies or other policies. And And then in the current system, there is a lot of cross subsidies, but we need to find new ways to deal with this, creating, for instance, lump sum or credits in the electricity bills. And this doesn't mean that we don't need to provide with efficient price signals. So if the price signal, the efficient price signal needs to be provided. If you are concerned about, and we should be concerned about low income, there should be explicit measures for these low income consumers. So saying that, that's a general overview. How I'm going to provide a closer look at the network cost recovery, how to do that, and what has been the proposal we have been doing. So if we apply, even if we apply the locational marginal pricing, this is one of the main messages I want to give you, is that we may have only what is, say here, the short-term marginal price surplus, and it's only one part of the network cost, okay? So that locational marginal price, because of the quadratic effect of losses, you may recover more than the only generation. You can pay part of the network cost with that, but it's a small part of it. In the studies we have done, I think this value could be around 20%. Of course, depends on the level of utilization and dimension of the network. And then you have the remaining network cost that has to be allocated, and how, again, network charges, how to do that. We need to decompose this in the two components I mentioned before. Then there is the long-term marginal cost, and these are related to future needs of the network and how to allocate those at the critical peak times, as I mentioned before. And then there is the residual cost, that these residual costs are the remaining network cost that needs to be recovered. And then again, they shouldn't distort both the short-term marginal cost and the long-term marginal cost signals. So how, if we have a methodology to do that, how we can do it? First of all, you need to have a cost segmentation and recognition. You know that utilities and network companies, they have recognized cost. There is a debate of how much is that efficient or not, but once they are done, we need to pay them. And we need to consider different principles. And of course, these principles sometimes are not, they are not aligned. So of course, economic efficiency should be one of the main criteria, but then we need also aspects about another principle, that is equity, as I explained before, and other about transparency. That okay, the methodology, of course, should be published and available to anyone. Then once we have the cost, we know what are the principles that should guide, let's say, the main principle on economic efficiency, and then how we can deal with equity problems. We need to apply the cost to customers or system users, and this can be consumers, as I said, including those that are active, only generators, storage. And how we can apply this, there are mainly three ways to charge for network cost: the energy component, capacity component, and also a fixed charge that is independent on the energy and capacity. I would explain some options there. And the final decision is how granular we want to provide these signals, and both in location and in time. As I said, we can go to the extreme, or we can stay at the transformer level, substation, or upper there. So just in more details, when you have network costs, how we can differentiate them, as I said, the long-term incremental cost, which way we can, according to economic efficient considerations, those needs to be applied based on the contribution of each users to the network peak, and it could be injections or withdrawals, and that at the end results in dynamic energy charge at peak time. So there some hours where the network, there is enough capacity in the network, then the charge may be 0. And when there is a big utilization of the network, the charge can be large. Then there is this temporal differentiation. And again, what is important at least is the voltage levels. That could be a possibility, but as I said, you can go even further down. And the locational differentiation, depending also on the temporal, depends, again, on the coincident, how coincident different consumption. There are clearly, for instance, for residential consumers, low voltage, maybe there are clear patterns where at night they go to dinner all together. So usually that peak happens specific hours at night. And then there is the locational differentiation. So it could be to the extreme, element by element, but other alternatives are possible. We have been making real applications of the methodology. In some cases, generally, we go at the voltage, different voltage levels. And then the residual cost, as I said, there is no driver really. How to apply this should be non-discretionary. Sorry, and there is no reason to make differentiation, temporal differentiations. And the locational differentiation is, it could be made at, for instance, at voltage level, because there is a cascade effect saying that, for instance, to supply the low voltage, you need medium voltage and high voltage networks. So those that are connected at low voltage needs to pay the corresponding of also the utilization of the upper level networks. So what are the alternatives? As I said, and it's a way to reconcile the efficiency with the equity principles. Here, just some examples and some criteria that you may want to consider. So the alternatives are, for instance, fixed charge based on income levels or their proxies. One of the proxies that we have discussed in the utility of the future, for instance, is the property value. So this basically at the end, the residual costs are kind of a tax. So we want to make them progressive, and the property value is a measure that sometimes is available. In some other cases, it's difficult to implement. That's why one of the criteria, the last one, has a negative sign. Another one is the contracted capacity charge. This, for some of you, may be strange. We have it in Spain. That's why we put it here as an option. In other places, that you need to contract certain capacity. In some other cases, just the capacity that by building codes are provided to different consumer levels. And then there is the fixed charge based on historical consumption. Okay? So of course, depending on the choice, there are difficulties. There is no one best option, and I imagine same as the market design. Sorry, has been said, we cannot have a solution that works well for everyone, but we can have a solution that is easier to implement in one place than other. And which criteria we want that the final solution fulfills. So first one is equity. So there is no discrimination. Sorry, we want to have discrimination among income levels, because again, this residual cost is kind of a charge. There is no causality. There is no efficient signal that we can provide with this signal. And the only one that fulfills this is to have a fixed charge based on income level or property value or any proxy of this. Another one is on economic efficiency. So we don't want that at the end we want, and this is, we want all the costs to be recovered. And here what we meant, because why this is economic efficient, if we have a system that is not that we cannot recover all the costs in the long run. At the end, it's not going to be, I mean, we don't want a system that go on bankrupt. So that's why all of these options should fulfill this. Then, of course, there is a minimization of cross subsidies. In some cases, for instance, if I put self-generation, some, for instance, I may reduce the contracted capacity, and that money that I'm not paying, other ones that don't have self-generation will end up paying. This is not for instance, if I put a fixed charge base on income or property value or any proxy, this is not related to the consumption, so that's fulfilled. I'm not going to explain the whole table, but just the criteria and provide some examples. For instance, how resistant is to storage. If I put a battery, I may be able to reduce the contracted capacity, so the maximum capacity that I'm requiring from the network. That is not the case in the other two options. How also is resistant to customer aggregation. So if I able to having, instead of one bill per customer, a whole building, and you aggregate all these buildings, so that the sum of the individual capacities is lower than the capacity of the whole building, the contracted capacity. So that is a way that also there is a negative, for instance, the second option is not as good as the other two. And as I said, the implementation barriers, how, for instance, adaptive to new customers. If I am have a charge based on historical consumption, if I don't have history of the consumer, that's difficult to apply. And also how easy is to implement. When we were considering, for instance, the property value in Spain, this is information that is confidential, and it was not, it's an information that the utilities, they don't have access to it, so that has some implementation challenges. Okay. What are some international experiences that are aligned with our theoretical proposals currently? Here, for instance, the UK is currently reviewing the tariffs to try to separate between this forward-looking and residual network cost. That is an example that is following the ideas of the methodology. Another one is in Spain, where we currently, thanks to the rollout of smart meters to all customers, now we have capacity charges that are changing also for different periods. In Norway, there is this separation between time of use energy charge that try to give signals when there are congestions in the network, and the residual cost. These residual costs are based on the contracted capacity charge. Or also in France, where also there is a time of use energy charges at peak times, and also there is a possibility that the DSOs can adapt this time of use charges whenever there is a local problem or local congestion in their networks. So this is a bit examples. They don't follow all the, let's say, the theoretical proposals, but there are movements that are taking place currently in those directions. Okay, so now I'm going to quite a different topic, and I think this is less continuistic than, I mean, it's more a continuation of the market design we have in Europe, but this has less relation, I say, with the US system and the previous talks, or even some aspects of the network charges I explained. But it's about the OneNet project. And I just want to say that this, we are about to finish one deliverable. Comillas, here we are leading it, but also Redes, one DSO, has been in the core team, and Vito Research Institute from Belgium also were partners. Sorry, the date there was not correct. I realized. So what is OneNet? OneNet is a quite big project. It may be the biggest in Horizon Europe. I don't have the data, but it's quite impressive, the number of partners we have. And Professor Antonello Monti from Fraunhofer and also Aachen University is the coordinator. I think Anto is connected. And the contribution from the European Commission is 22 million euros. So what is the objective of the project? Is to advance on the current European system, sorry. Today I'm having fun, maybe with air conditioning, sorry. That is advancing the current situation. So as I said, it's more continuistic, but trying to make it better, the current market design, and of course, smarter and more efficient. And how the main objective is how to coordinate in close to real time different markets, the system operation across countries. So this is quite a challenge as well, and maximizing again the consumer capabilities to participate in the market. A lot of focus on also on the consumer side of it. Also, this is for all of you. The project intends to be open to provide feedback from a wide range of stakeholders, and we have created this grid fund that is a forum where we present our results and when we share and get feedback from TSOs, regulators, aggregators, all the different stakeholders, as you can see in here. We will have the first meeting in September. The day is to be defined, but please register to our newsletter or follow-ups and also social media website so you can register to next meeting. One of the impressive aspects as well of OneNet, as I said, not only the amount of partners, but also the demonstrators. Currently, there are 15 demonstrators, so real implementations in a lot of, as you see, quite diverse in Europe. So we have these clusters, geographical clusters, where all these demonstrators are coordinated. And we are analyzing different market concepts, that is, and how they are implemented in real life operation. This is the deliverable I talk. I'm together with one colleague of mine, Mateo. We are leading it, but also with the contribution with other partners. We are in 2 days, we are submitting this to the European Commission. So soon it will be available also in our website. And what the main focus of this deliverable, there are 3 main objectives. The first one, of course, is to review what are the lessons learned from previous projects in terms of coordination models and market setups between transmission system operators and distribution system operators, define a theoretical market framework where we can advance on the developments on the market considering the current situation, the current design, and how to we can map this theoretical market framework with the different demonstration clusters, so we can analyze all this from the theory until practice and obtain conclusions about the implementation. Yeah, this is not that relevant, but what is, I think it goes in line with the objectives I described before. The survey, the theoretical market framework description, the mapping, and finally provide you some conclusion. Of course, this task is not in isolation. This is quite related to other work packages. This is the case in other projects. So we are getting inputs from work package 2, where it has reviewed best practices, the product definition, the business use cases. So what is going to be tested? So we're getting inputs from those and providing inputs on how, what are the market frameworks to the business use cases. Then we will continue the analysis. So in this task schedule 1 are the bricks and in next task, that is from the markets in isolation to the full coordination of all the different markets, and not only to procure system services, but also system services is equivalent to ancillary services for those from the US, but also to the wholesale energy market. Another task is going to look at the customer, how these markets are applicable to customers specifically. And at the end, in another task, we are going to address the challenges from after develop all these different concepts. We are going to have this implementation in real life. And finally, in Work Package 11, we'll provide the conclusions assessment for the whole project. Very briefly, it's not, I found it difficult to explain what are the markets without the products. As I said, this is another deliverable. I'm not going into the detail of it, but what is important, the main messages here are that the products are used to solve grid problems, system problems, not only at the grid. So all these markets for ancillary services, how to make it coordinated from the transmission system operators and distribution system operators, and how resources that are connected at the DSO levels, they can provide services, products to the TSO, and how to do that in a coordinated way. So for that, you need a product to be traded, that ancillary service that is decoupled in comparison with the US, where you co-optimize energy and ancillary service, but these products are decoupled. Of course, a challenge is how to define these products. So the first question will be, for which system operator this product is used? What are the relevant attributes? Here in attributes, what we are talking about, for instance, the activation time, the ramp of the products. So once the product has been called, how they have to be, what is the activation, and so on. What are the benefits? Which products can be harmonized and which products are not? There is a big discussion here on, should we have products that can be used for balancing, for frequency restoration, for instance, or frequency restoration reserve, and that same product can be used for congestion management. You can find a counter argument saying that if you are local, having the same requirements, the same activation time, very fast response, that will create a barrier for using flexibility that is local. And so, as I said, there are pros and cons of harmonizing the products. What aspects can be harmonized, and what are the values of these different attributes, as I said, ramping periods, full activation time, and so on.
Maybe so just to let you know, Jose, in order to ensure that we have some time for the discussion, it would be good if you finish within 3 minutes.
Perfect.
In order to
sorry for that. I'm about to.
Fine.
I'm not going. Yeah, I'm going quickly here for products and services. Just an example: those that are used for that are non-locational, using for frequency control, and those that are locational products. Then there is the market framework. I'm sorry that I'm not able to describe all of this, but maybe the main aspects. So there is one aspect that is about the entire market architecture, the number of markets, products, locations, as you have here, the coordination between the system operators, how to allocate resources among them. What is the market optimization if they are centralized, optimized both for both networks? Market operation, what is the remuneration scheme, how the market is clear, and how to incorporate the grid constraints. Again, in Europe, we don't, in the wholesale, we don't include the grid, we do it in subsequent markets or mechanisms. So that is sequential marketing instead of co-optimized. For that, we have to recluster the clusters. So that means that we look at those, in some countries, they look at the TSO, DSO market architecture, the different options that there are there. Others look more at the DSO focus, how to procure flexibility for the distribution operators, and the relation with the DSO is weaker. And there is other that focus more on technical aspects, for instance, communication exchange, and so on. From here, as I said, I don't have enough time. You can see that some different options. The situation is quite diverse. You will be overwhelmed with this table. It was just to show that let's say the approach followed is different between the countries. You have aspects about who is the buyer in different markets. Sometimes this only the DSO, or the DSO has priority over the TSO. That is one key aspect. If the bids are forwarding for the local market to a central market, and so on. Again, if you are interested in knowing any of these the details here, we can discuss later. And finally, the challenges. We try to derive what are current challenges based on all these analyses, and for each of the market frameworks, the pillars that we have defined. And as you can see, for instance, what is the relevant area of the markets, also the location between the principles. If you consider side effects of activation, so you want to make sure that when a product is activated to provide balancing services, not creating a problem at distribution level. So some of these demos are concentrated on these aspects: the bid forwarding, the timing of the different markets, the optimization, as I said, if it's centralized, decentralized optimization, what is the remuneration scheme, if it's pay as bid, pay as clear, many options there, and we are analyzing them, and how to include again the network representation. Of course, still we cannot have the full distribution network, so usually one option is to put constraints to certain elements that may create problems at distribution level. So thank you very much. Sorry for the minutes I took extra. And if you have any question, you can contact me, and please follow updates on the project in the project website.
Thank you so much, Marian, for the invitation. It's great to be part of this workshop. I'm going to be presenting some work, combining some of the work that we've been doing together with co-authors on renewables. So I'll be talking about investing in renewables. I'll be giving a more general introduction of the topic, of the main challenges that we face in current electricity markets, together with some results of a couple of papers that we've been working on regarding this issue. You all know that in order to reduce emissions in the overall economy, we first have to decarbonize the power sector. A necessary condition is that we deploy more renewables. So if you look at this report by ARENA, essentially by 2050, almost all electricity generation will have to come from renewables. This task has been made easier by the amazing technological progress that we have seen in the field of renewable generation. As you know, over the last 10 years, the cost of investing in solar PV have fallen dramatically by 80%. The cost of investing in wind have also fallen, not by such a large extent, given that it was already quite a mature technology. In any event, we can already say that renewables have become competitive vis-a-vis other conventional technologies. Part of this process, not all of it, but certainly some of it, has been driven by the use of competitive mechanisms, that is auctions, to procure renewable investments, and this has certainly contributed to adding competitive pressure to the whole value chain. We can refer to this as the renewable auction revolution, because over the last few years, many countries, more than 100, and this was the last count by ARENA. I bet that if we have more recent data, probably this number is still much bigger. So over 100 countries have already conducted renewable energy auctions. As I said, even though we cannot associate full causality to the use of auctions, I dare to say that part of the strong reduction in the cost that we have seen has been driven by the use of auctions, which at the same time have contributed to passing on the lower cost of renewables onto the final prices that consumers are paying for these new investments. One of the very last renewables auctions that has taken place, at least the one that I'm more familiar with, took place in Spain last January, when the regulator decided to auction off 3,000 megas of renewable investments. It was a technology neutral auction, but the regulator decided to add some minimum technology quotas. So at least 1,000 of those 3,000 megas had to be allocated to either solar PV and wind, with these extra 1,000 megas in between. They could have been allocated to any technology. So in essence, the auction worked as a technology neutral auction, but making sure that at least those 1,000 megas would go to solar and wind. This was organized as a pay-as-bid auction. The contract that was being auctioned off was the right to sell the electricity of these new investments to the Spanish electricity system at a fixed price during 12 years, which was the length of the contract. After those first 12 years, then the plants would simply sell the electricity in the wholesale market, at the wholesale market price. So this was the outcome of the auction. Out of these 3,000, 2,000 ended up in the hands of the solar producers, and 1,000 ended up in the hands of the wind investors. So at the end of the day, the outcome was a technology neutral auction, but just right at the allocation that would have triggered this minimum technology quota to be applied. As you can see, there was quite a lot of heterogeneity in terms of the winning prices of the various investors, which for me was kind of a surprising result, but one can find several theories that explain this heterogeneity in the winning prices. On average, the winning price was 25 euro per megawatt hour, and it was lower for solar producers as compared to wind producers. This is just the first of a round of renewal auctions that is going to take place during the decade. So the regulator has already published the minimum technology quotas of each of the various technologies for the next 5 years. So it would be very interesting to see what will happen in the next auction that will soon take place, whether there's any type of learning convergence or any difference in the type of bidding behavior that we have seen in this first auction. So why auctions for renewables? Why is it that we are switching from feed-in tariffs that, as you know, were used in the first stages of the deployment of renewables towards quantity instruments such as auctions? Well, let me just enumerate here some reasons why auctions seem to be a useful instrument in order to foster the deployment of renewables at least cost for society. First, it's clear there's a large degree of asymmetric information. Costs are rapidly falling down, and there's a lot of heterogeneity across technologies, across sites, across firms, and therefore for the regulator it is very difficult to set a single price and let the market choose the corresponding quantity. And auctions, we know they are a very useful instrument in order to overcome the asymmetric information. If we have investors competing before the project has been carried out, if we manage to have enough participation in these auctions will reveal competitive prices that reflect the average cost of the investments, because we are running these auctions before the investment has taken place. If we manage again to have enough competition, then these auctions will be able to select the best projects, the best technologies, and therefore also achieve productive and investment efficiency. At the same time, we would be facilitating entry of the new players, again, fostering more competitive outcomes. And auctions, they're in principle flexible enough to adapt the design of the auction to the specific needs that regulator might have. So for instance, if they want to use auctions to foster activity in areas where there used to be some coal plants that have shut down, maybe they could run auctions specific to a certain location. Or if they feel that they already have too much solar and they prefer to have some more wind or some other technology with a different production profile, they might have a flexibility to run technology-specific auctions. Some people ask, whenever I talk about auctions, why do we need any sort of support for renewables? If they're already competitive relative to gas and coal, why not simply use a fully technology neutral mechanism and let them sell their electricity in the wholesale electricity market with no additional support? First of all, I would not refer to auctions as support mechanisms. I would just refer to them as procurement mechanisms. Regulators have decided that they want to have a certain path of investment in renewables, and they use auctions as a way to allocate those investments. But there's additional reasons to that. One has to do with how much are we paying for renewables. We know that market prices currently reflect the marginal cost of gas, because gas is the marginal technology in most electricity markets in practice. However, in the future, if renewable goals are fulfilled and we manage to have carbon-free electricity markets, then energy markets will have prices that will converge towards the marginal cost of renewables, which are, as we know, well below the fixed cost or the average cost of renewables. In either case, energy market prices are going to be unrelated to the average cost of renewables. The resulting market prices that they are going to earn in electricity markets are going to be highly uncertain, highly volatile, and these would increase, it's already increasing, the cost of financing the investment in renewables, which, as you know, are highly capital intensive. In order to illustrate what will happen in future electricity markets, not very far away in time, I have plotted some data, which is probably not very different to what we're already seeing in California and some other markets. This is data coming from Spain. So I took data from 2019 because, for obvious reasons, 2020 data are polluted by the pandemic. So here what you can see is average electricity demand in Spain over the day, which is the yellow line. And the blue lines, they represent the pattern of solar production given the existing capacity in 2019, which is the lower line. But following the plans of the government, which is to increasingly invest more through auctions in solar PV over the current decade, we go up all the way up to the upper contour there that would represent solar production, average solar production in Spain during a representative day. And this upper line would represent what the solar production that we will get in 9 years' time. Clearly, all the solar production is concentrated during the same hours of the day, meaning that if we look at net demand, that is, if we subtract from market demand the production of solar PV, then we would get the famous DAC curve that we are already seeing in some of these markets, with prices being much lower during the mid hours of the day when solar production is at its highest level. It means that renewables will not only depress electricity market prices on average, but this price depressing effect will be much stronger at times when their production is higher. Given the fact that many hours of the day we might even have excess renewable production, that is more renewable production than total demand, this means that the prices, the electricity market prices for these technologies will quickly fall down to zero, therefore not allowing investors to recover their full investment cost. By backward induction, this might imply that very soon the incentives to invest in renewables will go down. So auctions are a way to manage, to achieve prices for renewables that better reflect the average cost of these investments. But once we have decided that auctions are the right instrument, that's only the beginning of it, because there's many different types of auctions that we might design, and all these different design elements have very important implications for auction performance as well as for the performance of the electricity market as a whole. So let me just list here some of the choices that we have to make when designing renewable auctions. First, we have to decide how much we want to auction, and we have to decide whether we want to publish a calendar of these auctions ahead of time, probably in order to foster the deployment of the value chain and the industry to get prepared to be able to procure all the necessary equipment for these investments. We have to decide as well whether we want to run technology neutral auctions, or whether we want to divide whatever auction volume across different technologies, what we would refer to as technology specific auctions. We have to decide which type of contract we want to auction off. For instance, we have to decide whether we want to expose producers to fixed energy prices, as the Spanish case just did, or whether we want to pay them according to some market premium so that they get to sell their electricity in the wholesale market. And on top of that, they get a positive or a minus fixed premium. Therefore, in that case, we would be exposing them to volatile prices. We have to decide as well whether we want to auction off energy or capacity. That is, whether we want to pay for energy or to capacity. And of course, we also have to choose the auction format, that is, the rules that map the bids into the set of winners, winning quantities, and winning prices. Clearly, all these choices have very strong implications for auction performance and market performance. And let me list here some of them. I've marked with an asterisk the ones I'll be providing more details about very soon. Let me just enumerate them. These choices have strong implications for market power in the energy market. In particular, I'll be focusing on whether price exposure, how price exposure affects the incentives of the investors and the owners of the new investments to exercise market power in the day-ahead market. Clearly, they also impact financing cost and entry of new players. So take, for instance, the example of whether we want to expose market players to fixed prices or to volatile prices. Typically, banks are going to ask for more stringent financing conditions and higher financial cost if the investors are facing more risky prices. So we go for fixed prices that remove some of these price volatility from the investors. Typically, financing costs are going to be lower, and new and smaller players might be more willing to enter this market than otherwise. The location of the new investments is also a very important decision that might be affected by these choices. Take, for instance, the example of whether we pay for capacity or whether we pay for energy. If we pay for capacity, this means that 100 mega, they get the same payment regardless of whether they're located in a windy or in a sunny place, or whether they are located in places where the natural resource is not very abundant. If that is the case, then location decisions are not going to be as efficient as if we pay for energy, in which case, clearly places where the resource is more abundant will be able to receive higher market payments, and therefore they would be able or willing to bid in lower prices in the auctions. So either we pay for megawatts or we pay for megawatts per hour clearly has a very important implication for location decisions. But at the same time, because there's more heterogeneity in the bids when we pay in terms of energy, because to the heterogeneity in the cost of investments would add the heterogeneity in the production of the various sites, typically the bid functions tend to be steeper, and therefore the rents that the winning suppliers get if we offer contracts that depend on energy tend to be higher than in those cases in which we are paying for capacity. So clearly all these choices face the regulator with a trade-off, and in every particular context, the regulator will have to take these choices, taking into account the specificities of each case. So for instance, there's countries in which there's not a lot of heterogeneity in terms of the production of the various sites, whereas there's other countries in which this heterogeneity is higher. So taking into account all these specificities, the regulator would have to go for one design or another. An important issue as well has to do with which renewable technologies are chosen, and this also depends on the type of auction design that the regulator chooses, as I will explain in more detail in what follows. In order to provide some insights as to the impact of auction design on market power and technology choices, let me go through the main results of two papers that we've been recently working on. I'll be simply be providing the main insights, and if it's not sufficiently clear or if you want me to expand on it, on any of them, I'll be happy to do so at the end of the talk. Let me start with the first paper, technology neutral versus technology specific procurement, in which we try to understand when it is optimal for the regulator or when it's preferable for the regulator to go for a fully technology neutral approach or rather a more technology specific design. For that matter, let me give you a small, short overview of the main model that we developed in the paper, which is the simplest version that we could think of in order to capture the main trade-off when it comes to relying on one type of option or another. So think of one good, let's call these renewable investments that can be produced, provided with two technologies denoted by T, either technology 1 or technology 2, and these technologies can be provided by a continuum of risk-neutral price-taking suppliers. This means they do not have market power and they're willing to provide these investments at their cost. What are their costs? Well, their costs are represented by this quadratic function where Q represents the amount of the investment. These technologies have different costs. They're affected by a technology-specific parameter, which is known, CT. So we assume that technology 2 is ex ante more costly than technology 1. So we use delta C to denote the ex ante cost difference of these parameters across technologies. But they're also subject to some idiosyncratic shocks that are technology-specific and that are not known by the auctioneer, by the regulator, but they're known by firms. So the uncertainty over these thetas is reflecting this degree of asymmetric information. The regulator doesn't know all the information regarding their cost. All he knows is that in expectation, these shocks are white noise. They're zero in expectation. They have some variance sigma, and they might be correlated across the two technologies where the parameter rho is capturing the degree of cost correlation across these technologies, which could well be positive or negative. Whenever we invest in these technologies, we obtain some social benefits. For simplicity, we assume that the social benefits provided by these two technologies are completely homogeneous. So the regulator just cares about the total amount of renewable investments in the system, but not about the composition of these investments. And this is something that we could easily extend to allow for some differentiation in terms of the benefits that these technologies provide. So our regulator has to choose which type of auction format to use in order to procure these two technologies. And he also has to decide how much to procure, and so on and so forth. So the general way to write down the regulator's objective function is simply to say that the regulator wants to maximize expected welfare that depends on these gross benefits, on these social benefits, taking into account that the investments are costly. So this term here represents the cost of the investments, but also taking into account that the regulator dislikes leaving very high rents to the investors because these public costs that are devoted to paying for these investments are costly. In order to get funds to pay for these investments, we have to impose taxes in the rest of the economy, and there's a distortion associated to those taxes. So the lower the amount of rents that we leave with these investors, the better. And this is captured by this parameter lambda that is reflecting the social cost of public funds. So if we assume that lambda was 0, this term would disappear, and the regulator would simply like to maximize full efficiency measured by the difference between social benefits minus social cost. Whenever lambda is positive, it means that on top of that, the regulator aims at minimizing the rents left with the retailers. By the way, I forgot to mention that capital T represents the total payment that the regulator makes through the auction for procuring this total amount of investments. In the paper, we start by characterizing the optimal mechanism, that is, characterize the optimal way for the regulator to procure these technologies. We describe the properties of this mechanism. The optimal mechanism somehow allows the regulator to overcome this asymmetric information. The total quantity that is being auctioned off adjusts to these cost shocks. The quantities that are allocated to each technology, as well as the prices that are paid to each of these technologies, also adjust to these cost shocks. However, in practice, we don't see that regulators, at least as far as we are aware of, are really using this type of optimal mechanisms. In practice, they tend to use simpler mechanisms that don't give them any type of flexibility regarding the total amount of investments that are being auctioned off. So for instance, the Spanish renewal auction just gives one example. The Spanish regulator committed to auctioning off 3,000 megas. So it was not optimal in the sense that it was not letting the total amount of investments to adjust to the bids that were received in the auction. And this type of mechanism with fixed, ex-ante fixed total quantity is very common in practice. So after characterizing the optimal mechanism in the paper, we characterize the solution under the simple mechanisms that are used in practice, and we compare the properties of those mechanisms with the properties of the optimal mechanism, which for the sake of time, I'm not gonna be doing here. I refer those of you who are interested to the paper. I'll simply describe and compare simple technology neutral and technology specific mechanisms to try to understand what is the trade-off when choosing between these formats. So what do I mean with a technology neutral mechanism? Well, simply the regulator chooses how much she wants to procure through the auction, the total quantity, and then the market, that is the auction, will deliver what is the market clearing price for that quantity and what is the allocation across these two technologies. So if we are thinking, for instance, of wind and solar, how many investments are gonna be wind investments or solar investments? This is in contrast with technology-specific auctions by which the regulator commits to one technology allocation ex ante and runs two separate auctions for these two quotas. So each of these technology specific auctions, one for solar and one for wind, will deliver a possibly different price across these two auctions. These two simple mechanisms clearly do not allow the regulator to extract the symmetric information that the investors have about the idiosyncratic shocks, and therefore they face the regulator with a rent efficiency trade-off. And what we find is that if the regulator wants to maximize cost efficiency, that is, make sure that the least cost investments are carried out, then she should favor a technology neutral approach. However, we also show that this technology neutral approach gives rise to high rents, the more asymmetric the cost across these two technologies are. And therefore, if the regulator is concerned about reducing rents, maybe because the social cost of public funds is very high, then she should rather go for a technology-specific approach that will give up some degree of cost efficiency with the benefit of reducing payments to producers. Let me give you an overview of how we derive the main results of the paper, and then I'll give you a graphical illustration of those results. So let's start with technology-neutral auctions. As I said, the regulator chooses the total amount of investments that she wants to have, let's say 3,000 megas, and then the auction will determine what is the market clearing price and what is the allocation of these investments across firms. Because firms are price takers, the market clearing price will be such that the marginal cost of these two technologies are equalized, giving rise to an efficient allocation. And the market clearing price in this auction will simply be equal to the marginal cost of these two technologies. If we solve this equation, we can simply write it in the following way to understand how much is allocated to the ex-ante low-cost technology and how much is allocated to the ex-ante high-cost technology. So the low-cost technology will at least get half of the total quantity that is being auctioned off, and it will get an extra amount, fee n, which is somehow capturing the ex-ante cost difference across these two technologies. So if ex-ante technology one is really less costly than technology two, this additional quantity that will be allocated to technology one will be higher. But of course, because the allocation is decided exposed through the bidding process, these bids and therefore the allocated quantities will also adjust to these cost shocks. So if the exposed cost shocks are such that technology one is even less costly than technology two, then technology one will get an extra plus to the quantity allocated to it. But keep in mind that these cost shocks can also become, the difference between these two cost shocks might well become negative, therefore reducing the ex-ante advantage of technology one. Okay, so we'll have a market clearing price reflecting these cost shocks, reflecting the marginal cost of these two technologies, and an allocation that is going to be efficient. So let me simply show this graphically. So this is the price quantity axis. This is the total quantity that is going to be auctioned off. We might think of these as the marginal cost of these two technologies, technology one and technology two, given these cost shocks. With these being the total quantity, the market clearing price will be here. And at this price, the marginal cost of these two technologies are equalized, giving rise to the allocation across these two technologies. Because these two technologies get paid at the same price, at the technology neutral price, these shaded areas will simply represent the payments that we make to technology two, that gets the smaller share of the total pie, and to technology one. So let's see what happens if we instead rely on a technology-specific auction. If we rely on a technology-specific auction, the regulator has to commit ex-ante to one quota for technology one and one quota for technology two, run two separate technology-specific auctions, and therefore get two technology-specific prices. The issue is, how is the regulator choosing these technology-specific quotas? Well, what she wants to do, she wants to minimize the marginal social cost she wants to minimize the social cost of this investment. So what she's gonna do is she's gonna choose Q1 and Q2 ex ante in order to equalize the marginal social cost of these investments. In the technology neutral auction, we just saw that the allocation is such that the realized marginal costs are equalized, but here what we are equalizing is this marginal social cost, keeping in mind that the payments that we give to these technologies are costly because of this positive social cost of public funds. If lambda was equal to 0, this term would totally disappear. So the regulator would be choosing Q1 and Q2 in order to maximize the expected marginal cost. That is in order to try to achieve ex ante efficiency. But whenever lambda is positive, she's willing to distort the allocation away from the efficient allocation in order to minimize the payments given to these firms. Why? Look at this term. What this term is telling us is that whenever we increase the allocation to technology one a little bit, the price that we're gonna pay to that technology goes up, and therefore the rents that we're gonna pay to these investors in this technology also go up. And this equation is taking into account this impact, and therefore is trying to reallocate the quantities in order to minimize that effect. The resulting—
Natalia,
yeah?
we have 5 minutes left, just to inform you.
Okay, that's very quick. Thank you so much, Marian. I'll do my best. So the resulting allocation can be written in a similar form as I did before. In particular, technology one gets half of the total allocation and then gets an additional plus. But this additional quantity that is given to technology one is now distorted as a function of the social cost of the public funds. Indeed, the higher lambda, the more costly these funds are, the smaller is the additional quantity that is allocated to technology one, precisely in order to minimize the total payments that this technology gets. We can see this graphically. So this is the same type of figure that we saw before. This is the allocation under the technology neutral auction. Now the solution under the technology specific approach is such that we are allocating less to the less costly technology. And we do so in order to reduce the price from this dotted line to this dashed line, to reduce the price that we pay to the low-cost technology, which allows us to save all this area. This comes up the cost of having to increase the allocation to the more costly technology, which implies that the price for technology 2 goes up. But the solution is such that the increase in payments to technology 2 is much lower than the savings in payments because of the reduction in the price for technology 1. Overall, this implies that if we design technology-specific auctions properly, we would manage to reduce payments at the cost of distorting the allocation from the efficient one, and therefore giving rise to higher investment cost. If we compare the resulting welfare under these 2 auctions, we get to a formula like this. Let me try to shed some light on what this formula is telling us. This formula is computing the difference in terms of welfare when the auctioneer is using technology neutral auctions versus cases in which the auctioneer is using a technology-specific auction. And what this formula is telling us is that when this difference is positive, it means that it is better to go for technology-neutral auctions, whereas when this difference is negative, then welfare is higher when we go for technology-specific auctions. The 2 terms in brackets are determining the sign of this difference, and they're capturing this rents efficiency trade-off that I mentioned before. In particular, the first term is capturing the greater efficiency of technology-neutral auctions, whereas the second term is capturing the ability of technology-specific auctions to reduce total payments. So it's given us some information as to when the regulator should be going for technology neutrality and when she should not. For instance, technology-specific auctions dominate technology-neutral auctions whenever the principal has quite a lot of information regarding the cost of these technologies, in which case the variance of these cost shocks almost tends to zero, so this term fully cancels out. Or if the cost shocks of these technologies are very highly correlated, in which case the efficiency benefit of technology neutral auctions is not that high, and therefore the payment reduction property of the technology specific approach dominates. Or technology specific auctions also dominate if there's a very strong concern for rents, that is if lambda is very high, in which case this term is really very heavy, or if the technologies are so asymmetric ex ante that the resulting rents for the low cost technologies are gonna be very high. In the paper, we analyze other simple mechanisms that are used in practice, including the one used by the Spanish regulator, where she was running, as I said before, a technology neutral auction with technology specific quotas. And we find that this choice of technology neutrality plus technology specific quotas seems to perform very well relative to other mechanisms, because with the quotas, we end up in a technology specific situation precisely in those cases in which the cost differences are so large that given rents would be very costly. But at the same time, we are given some flexibility so that if the cost shocks are not very apart from each other and the technologies tend to be more symmetric, then the outcome would be the same as the one under a technology specific, the one under technology neutrality. Unfortunately, I don't have time to cover all the material that I had prepared for you today. I was hoping to be able to tell you something about the effects of exposing renewables to price volatility or not, the cons and the pros of doing so, but I leave it for the discussion. Let me just conclude by saying that clearly I believe that the deployment of renewables implies that market performance is challenging, and therefore we probably have to address this through market design. I believe that auctions for renewables, and not only for renewables, also probably for storage solutions and for backup capacity, provide a very suitable instrument to address some of the challenges faced by future electricity markets. I believe, if I may, that we all have to contribute to this debate. In particular, I believe economists and industrial economists and game theorists and experts on auction design have much to contribute by providing insights that have to do with the relevance of incentives, with the importance of market rules and auction rules on strategic behavior, and on the ability to be able to properly measure the effects of the various policies, because I believe we'll have to be learning throughout this process, and being able to measure those effects will be very useful for this learning process. So thank you very much, and I'll be happy to answer any questions you might have.
Okay, so thank you very much, Marianne, and thank you very much for the opportunity to the organizers to present. What I'd like to talk about is what are called, I would call purely financial participants. And these are entities that are, don't own any generation, don't own a distribution network, essentially, for the most part, don't own any physical assets in the industry. But they have, at least in the United States, been a disruptive force in the industry. One of the more famous disruptive forces is the Enron, but I think that many of the things that they've done, the follow-on financial players are, I think, have the potential to improve the performance of the market. And so what I'd like to talk about is exactly that issue, which is, you know, why their role, I believe, needs to be fostered and why it is going to potentially yield benefits. And then I'll present along the way a lot of results from research that I and others have done that I think buttress that case. So what's been happening in the market is certainly in the United States is a growing share of intermittent renewables and a increase in energy supply risk. So and I emphasize here, this is where we've seen retirements of conventional dispatchable resources. So for example, California, you can see that we retired, almost more than 10,000 megawatts of dispatchable thermal generation and replaced it with a little bit, less than 9,000 megawatts of solar and wind. And that could be part of what's going on in terms of what we're seeing in California. And then in Texas, a significant reduction in coal and nuclear with a large increase in wind and increase in solar and a bit of natural gas. So this has certainly increased this energy supply risk, which has led to wholesale price volatility. In August of 2020, we saw this in California, and in February of 2021 in ERCOT. And the other thing that this does, this increasing intermittency, is it increases the relevance of the way I would describe it as non-convexities in the market operation. In other words, you're starting up units more frequently, you're operating at minimum safe operating level, you're constrained on ramp rates more frequently. These are things that are operational challenges as well, but also can lead to price volatility. And so what this suggests to me is that there's an increasing role for financial market participants to manage this energy supply risk through both the hedging instruments they provide, and which then implies the commitments that get made to physical resources, short-term price risk, and again, similar thing, as well as managing these non-convexities. But in order for this to happen, you need a market design where financial participants can improve industry performance and not degrade industry performance. And that's where I think a multi-settlement locational marginal pricing market comes in to do that. So what I would like to talk about is first just to give you a review of the renewable energy uncertainty that we've been seeing, we see in California, and then talk about what are the features of this LMP, multi-settlement LMP design that can allow financial players to improve industry performance, and then go through some examples of how I think they can, and how I have some empirical evidence that they have done so. And this slide lists a number of those instances. So what does the distribution of renewable energy production look like in California? Here is a graph of the histogram of hourly wind and solar output in 2020 in California. And just at the bottom, you can see I have the capacity of wind and the capacity of solar in 2020. And you can see that the important thing to emphasize is that the bar that's close to zero is not zero. In other words, the modal outcome of solar is zero production or near zero production of solar, as you can see, but no zero solar production. That, as you can see there, occurs 41% of the time. So this is the hourly output conditional on a positive output from the resources. So the other thing you can see with respect to wind is, even though we have about 6,000 megawatts of wind, we never get anything close to 6,000 megawatt hours in any hour from the wind units. Whereas with solar, for a few hours a day, we get pretty close to what is the capacity of the solar on the system. And this is just the histogram of the combination of the intermittent renewable output. And again, you can see a small fraction of the hours a year, you get zero output from any renewables, but more importantly, you know, the modal hour of the year, you're getting very little output from the renewables. And in fact, this is giving you the various sample statistics on this. I would at least sort of refer you down here to see that even though we have 20,000 megawatts of wind and solar in the system in California, 50% of the hours of the year, we're getting less than 3,300 megawatt hours out of that capacity. So there's just and then you can see that sort of various standardized measures of volatility have actually been going up. You know, for example, the coefficient of variation, which is the standard deviation divided by the mean, has been sort of rising over time, as well as the skewness, meaning the extent to which you get that long, this long tail here in this diagram has been also going up. So why does this happen? This happens in California because we are a, you know, very tall north-south state, and the sun goes east-west, and we are a coastal state where we have an ocean on one side and essentially mountains on the other. So you get, you know, these temperature gradients. And so what you can see, and this is a reference to a paper of mine that looked at across the 53 wind and solar locations in California, what was the contemporaneous correlation across locations in both solar output as well as wind output, and the combination of the two. And there is a massive amount of contemporaneous correlation between the production. Basically, it's a sunny day in California, you get lots of solar. It's not a sunny day in California, you get very little. Similarly with wind, although with wind there's a little bit less correlation, but for the sort of linear algebra folks in the audience, the first eigenvalue of the contemporaneous covariance matrix for solar is roughly 90% of the total variation. So you have a large amount of contemporaneous covariance between the hourly capacity factors at the various locations. So the other thing that I think is important to emphasize as to risk management is the durations of low levels of output. In other words, you know, long periods where you get very little output. And what we do here is we say, okay, let's take a given level of production of wind and solar energy, and let's ask the question of when do we pass through the threshold that we've set. Say we set that threshold at 8,000 megawatt hours. How many hours do we go consecutively where we keep getting less than 8,000 megawatt hours? And then how long is it until we cross back up above that threshold in terms of wind and solar production? That's what we're talking about here. So again, to take the example of 8,000 megawatt hours in 2020, you can see that we have 325 durations where you got below 8,000 megawatt hours for at least 1 hour. The mean length of that duration was about 19 hours, roughly a day, but it had a large standard deviation. And what you can see is that the maximum was 139 hours, which is, you know, roughly about six days that you could, you know, have very little wind and solar production. So there is a considerable amount of this, you know, very potential for long durations of low renewable output as well. That's going to require managing as well. So, what are the features of a wholesale market design that these purely financial participants can essentially participate and improve? Well, it is essentially it is a locational marginal pricing market, and this just gives you a little history of restructuring in the United States, in particular, PJM, California, New England, and Texas all started with very similar market designs to which currently exist in Europe, in the sense of single zone pricing or small number of zone pricing, and assuming essentially a copper plate transmission network within a given zone or market, and then essentially a redispatch process to make the schedules that emerged from this financial market, simplified financial market physically feasible. And at least what we found in the United States in all the markets is this congestion management process certainly led to massive numbers of opportunities for inefficient behavior. PJM was the first. Their market basically just completely crashed right out of the box. And they had to quickly scramble to implement a market that priced all relevant operating constraints. And so the big lesson that we've certainly learned from the US is this need to capture the reality of how the transmission network and generation units operate in the market model. And any difference between these two things essentially leads to behavior that degrades market efficiency. And the way this occurs is it's not unique to American markets. It exists in all of these markets around the world. For example, in Colombia, they have a negative positive and reconciliation mechanism. In Australia, they have a constrained on and constrained off generation. These are essentially ways to manage this congestion within the pricing zone. But what you get is you get this so-called, what we called in the United States, the debt game, where what I do is I know that I can't operate in real time. So what I do is I offer in at a very low price in a zonal day-ahead market because I know I can't deliver the energy in real time, but I get taken because it's a simplified market. And then I get paid the market clearing price for this energy. And then since it can actually operate, the system operator's got to come back to me and say, you know, would you be willing to essentially buy this back? And I say, sure, I'll buy it back at a lower price. And so I essentially get paid the difference between the price I sold it at and the price that I buy it back for essentially producing no or little energy. In the ink game is essentially the opposite of I know I'm needed. And so what I do is I offer an extremely high offer price. And sure enough, the system operator doesn't take me in the simplified market. And then I find out that, okay, you're going to need me. And so I get paid as offered at this higher offer price in the redispatch market. And again, this is not, as I said, unique to US markets or other markets. This an example from a paper done on the Italian market sort of shows how this works and how suppliers in that market understand when they're likely to be not needed and therefore bid very low offer price in the day ahead simplified market, or know they're going to be needed in real time, bid very high in the day ahead simplified market in order to essentially earn higher profits from doing so and imposing significant costs on to consumers. So the basic lesson is from the US experience is this in real time physics wins. The reliability, realities of how the grid operates is essentially known, and market participants are going to take advantage of it. And the big reason I think that this showed up in the US is that in the US, we pretty much made very little investments in transmission from between the early 1970s and the early 2000s. So this left most of the regions of the US with transmission networks that were very poorly suited to operate a wholesale market that had essentially assumed very little transmission congestion. What, as the last bullet point on the slide states, a successful zonal design requires a transmission network in each zone that makes all generation units equally effective in a electricity sense at serving load at all locations in that zone. That just was not true for all of the US markets, largely because of this issue of the lack of transmission. And essentially you need to make this commitment And the good news, at least in the case of the Europeans, is these were, for the most part, companies that were national champions that had probably invested a significantly more in transmission upgrades than the regions in the United States had. And so this sort of reality was closer to truth in the European context than it was in the US context. But I think the interesting question is going to see is that what's I've written here, which is this commitment is certainly harder to keep in a market with a significant amount of intermittent renewables, largely because patterns of congestion and the like are much less predictable because you've got a lot of intermittent renewables hitting the system. And so that is it's not like you always know that the cheap thermal generator is located here, the more expensive peaker generators located there. Congestion always goes from one to the other. With intermittent renewables, loop transmission network, you're going to get a lot more uncertainty. You're going to have to invest a heck of a lot more. My favorite example of this is Alberta, the province of Alberta in Canada, that made effectively a commitment under a single zone market. They essentially said, we will commit to transmission upgrades in order to make the incidence of congestion as infrequent as possible. And as you can see, it gets extremely expensive, even in a region like Alberta, which has not a lot of population, but basically needed to build out its transmission network to ensure that the congestion was infrequent. That's a quite expensive transmission charge that they are essentially charging off of relative to that charge load. So it gets really expensive to pursue such a strategy. So what the US, as we said, has done is adopted this locational marginal pricing, which is pricing all transmission constraints and also co-optimizes the procurement of energy and ancillary services. I suspect other speakers have talked about this, so I'll skip over it. But the big issue is this pricing of all transmission constraints in the day-ahead and real-time market. This exists in California. All of these places in the United States, remember Canada does not, and neither does Ontario, but all of the US markets use locational marginal pricing. So the big thing that it does is it doesn't allow this infeasible schedule, meaning it does not allow the guy that knows that he's not needed to get scheduled in the day ahead market, or the guy that knows he's needed not to get scheduled in the day ahead market. And the other thing that it does is it allows three-part offers so that you can have, startup, no load, energy cost. And what then happens in the day ahead market is you can find that least cost mix, the least cost solution to this mixed integer programming problem to serve demand at all locations in the network, taking into account all of these constraints. And then finally, the co-optimization of energy and reserves, different from what was initially the case in a number of US markets of sequential clearing of energy and then ancillary services. That significantly reduced ancillary services costs relative to sequential. And just to give an example from California, early in California, the ancillary services markets cleared after the day ahead market closed, before the real-time energy market operated. And so essentially, suppliers knew that, the stuff that was taken to supply energy in the day-ahead market could not compete to supply ancillary services. And so they could significantly raise prices in the ancillary services market. And as you can see, the first 3 years in the market in California, those costs were 13, 5.7, 6.8, whereas now we've switched to this locational marginal pricing with a co-optimized energy and ancillary services market. And even though we've increased the amount of renewables in the system to roughly 30% in these years, the percent of total energy costs that are coming to pay for ancillary services is never been greater than 2% in any of the past 3 years listed here. So this co-optimization really helps to reduce those costs, as well as just the other, to put a plug in, is more frequent settlement of your real-time market. So for example, in the California market and all the US markets, settlement, meaning the real-time market, operates every 5 minutes. And so that also helps to reduce the need for operating reserves. So the big thing about this is we're trading in the day-ahead market purely financial commitments that have implications for real-time market outcomes. In other words, what I schedule in the day-ahead market, I get paid for. So if I sell 40 in the day-ahead market, that's $1,000 I get. But if I do not actually produce the 40, then I essentially must purchase what I don't produce in the real-time market to make up my commitment to sell 40 in that day-ahead market. I got to buy that to replace the 10 I did not supply at the real-time price. Additionally, if I'm a buyer and I buy, again, I buy 1,000 megawatts, 40 megawatts of energy, I'm paying $1,000. But if I only consume 30, then I'm effectively selling that 10 megawatts that I did not actually consume at the real-time price. And so this redesign, this is just citing some work that I've done looking at the process of the transition from a zonal multi-settlement, day-ahead zonal market, real-time zonal market, to a multi-settlement LMP market, sort of for the same amount of energy, thermal energy dispatched. We managed to do that using 2% less fossil fuel, a variable cost of 2.1% less. This adds up to more than $100 million in variable cost savings associated with this transition. In Texas, this transition was even more effective in the sense of total cost of dispatching system fell by almost 4% as a result of this you doing a locational marginal pricing day-ahead market and real-time market versus the existing zonal market at the time. And this penciled out to about $300 million of annual savings in these costs. So these are non-trivial savings associated with this transition. So how do purely financial participants factor into this market, and how can they make it work better? Well, the first way that I think they can do this and is through what's called virtual or convergence bidding. This exists in all of the LMP markets in the United States. And the way this works is you, as a purely financial participant, you can put up your collateral at the ISO for the amount of money that you would like to bid in value that you'd like to bid in virtual bids. And you're then allowed to submit virtual bids just like a generator. And at any location in the network in the market. Now, there are restrictions on locations that you can submit virtual bids, but there are literally thousands of locations in California that you can do this, and similar magnitudes in other markets. And what you can then do is you submit this virtual bid. It can be an Inc, which says what I'm doing is I'm willing to sell energy just like a generator in the day-ahead market. I submit an upward sloping offer curve for selling energy. And then if I win, I have to essentially undo whatever I sold in the day-ahead market at the real-time price. So as I list here, if I sold 1 megawatt in the day-ahead market as Inc, then I'm going to earn the difference between the day-ahead price and the real-time price for that transaction. Similarly, if I submit a DEC, what that means, I'm effectively buying energy at that location in the day-ahead market, and my profit then is the difference between the real-time price and the day-ahead price, because when I buy the energy, I essentially then sell it in real time at the real time price. And the important thing to emphasize here is that these bids are treated exactly like bids of physical resources in the day-ahead market. Now, in real time, the system operator ignores the demand side of the market in the sense that it dispatches the system physical resources to meet the actual demand throughout the transmission network. So in other words, it is only dispatching physical resources in real time to meet actual demands throughout the network. And so the way that you make money as a virtual bidder is your ability to essentially anticipate and perhaps even contribute to improving the real-time dispatch. So essentially, the real-time virtual bids, one of the reasons they're called convergence bids is because they are at least designed to converge day-ahead and real-time prices. But I think the more important thing that they can do is they can improve the efficiency of the short-term market. And in particular, improve the ability of the market to essentially solve extremely complex mixed integer programming problems to dispatch the system when there are lots of operating constraints that are likely to be binding. So take an example. So I may have a low variable cost but long start unit that doesn't start in the day ahead market. And if it's not started in the day ahead market, it can't operate in real time. In particular, this is because there are a number of units in California that have an extremely long startup time. And what will happen instead is you'll have to start up a short start, higher variable cost unit to operate. Well, if a purely financial participant somehow believes that essentially that unit really is going to be needed at that location, it can submit a day ahead bid into essentially a deck bid at that location, which increases the demand at that location enough to get that long start unit committed, that then reduces the day ahead price and potentially increases the real-time price slightly above that. So this virtual bidder, makes money from essentially the fact that he bought energy in the day ahead market and he then sold it in the real-time market. And similarly, another thing that happens in most of these markets with a lot of renewables is that the intermittent renewable resource typically underschedules relative to their expected production. Why? Well, largely because if you end up short, because of that very large positive correlation that I talked about, if you're a wind resource and you ended up being short relative to your schedule, the price could spike to an extremely high level. You have to buy out of the short-term market to essentially replace what you scheduled in the day-ahead market. That's not a risk you'd like to take on, so you're just going to hedge your bet, and you're going to underschedule relative to your expected output level, but essentially minimizing, if you like, balancing your expected loss from underscheduling against your expected benefit from underscheduling, and do that. Whereas what can happen is virtual bidders can then say, well, we have a little bit more risk tolerance because we can diversify perhaps across locations. We're going to sell an ink at the locations in the day ahead market that essentially pushes up the amount of energy at that location, anticipating how much wind is actually going to come. And if we're right, we're going to essentially make the difference between day ahead and real-time price in terms of that. And once again, no need for a thermal resource to start up to get committed to raise the cost, and therefore instead get if you like, a day ahead schedule of generation resources that comes closer to achieving the least cost dispatch in real time. And so this is just summarizing some results from a paper that we did on California looking at this, and we found that the introduction of virtual bidding essentially reduced difference between day ahead and real-time prices, as one would expect. But more importantly, you get a smaller variance in day ahead prices, smaller variance in day ahead real-time price differences. The other is that essentially the introduction of virtual bidding eliminated any sort of correlation in the vector of day-ahead real-time price differences beyond the first day, largely because that's information that you could trade based on. Price differences beyond the first day. On the first day, you can't trade on, because what is happening in the day-ahead market today is the real-time market for the current day. And so there's no way for you to actually take advantage of that. So essentially,
Frank?
Excuse me?
So, sorry, could I interrupt for a question here?
Sure.
I was just wondering what information is given to financial participants? Like, do plant owners have to submit a planned schedule before making bids, or is it only learning from past results?
Yeah, no, bids are confidential of all market participants, so virtuals as well as physical players. But there is information out there in terms of what people are producing, what weather conditions are. There, for example, the entities that bid on wind, a lot of them are very good at essentially weather forecasting and the like. And they factor that information in terms of the information that they want to provide. The other is that, just simply as well, doing what, pure finance players you'd expect do, which is look at, sorts of things like inertia and price differences and the like, which is why I would guess that what happened with the introduction of virtual bidding is any sort of information about future day-ahead real-time price differences was immediately, sort of eroded away as a result of the introduction of virtual bidding, because that information is something that you could have traded on, and what happened is that traded away. So the other issue is the more important thing is the fact that we also measured an improvement in market performance, in the sense that particularly during periods, what we defined various measures of high stress system conditions when lots of non-convexities were relevant in the system solution. We found essentially a lower cost to dispatch the system relative to the cost before the introduction of virtual bidders. So and then, even as well, we also documented that, reduction in carbon emissions. So you could say, financial traders are also environmentally conscious, but that would probably be disingenuous. Okay, so financial transmission rights are another thing that financial players can participate in. These are essentially assets that essentially pay out, not per FDRs. Purchasers, sorry, not peers, receive the difference between the price at the end point and the price at the start point times the amount they purchased. And what these FDRs do is they allow market participants to hedge locational price differences. So what it means is I can receive the price at the gen node if I have an FDR from the gen node to my load node. And one of the things that financial players do is in the FTR auctions, they participate. And what they're attempting to do is essentially buy undervalued FTRs, meaning FTRs they think that will have a payment stream that is greater than the cost of the FTR, or sell overvalued FTRs, meaning sell FTRs that have a payment stream less than the price that the FTR trades at. And what we hope then is we get more accurate pricing of the FDRs that then physical market participants will use these FDRs to then negotiate deals with a lower cost sources of supply in the network, and therefore yield a lower cost dispatch of the system in terms of, or at least more aggressive behavior from market participants and lower prices to consumers as a result of the hedges that have taken place. Now,
sorry again. So does a TSO submit any prediction of scarcities in the grid, or?
No. Again, this
nothing.
Is just simply, again, locational price differences. For the FDR auction, the TSO, the transmission system operator or market operator, makes available typically what's called the network model that is used for the FDR auction, so that market participants can essentially know and play around to figure out how they might want to bid. But once again, it's just all market participants. Periodically, these auctions get run, and they essentially compete to buy these FTRs again between the locations that they are interested in. All right, so that's one. This is sort of ongoing research at the moment, looking at this question to see, are there market efficiency benefits associated with the actions of FTR players? The other one is looking at the competitiveness benefits of introducing purely financial participants in wholesale retail market. This comes from Singapore. So in 2015, Singapore introduced an anonymous futures market into their electricity market, which is also an LMP market, where essentially you could buy what was called forward contracts that cleared against what's called the USEP, Uniform Singapore Electricity Price. And the issue that we were interested in looking at is, did the introduction of these standardized forward financial contracts lead to lower retail prices? So how would that work? Well, that would work in the sense that I, as a purely financial retailer, I pair up with a bank. I then buy a futures contract for a delivery horizon, and then I bid in the retail procurement auction for a retailer, one of the free retailers in Singapore, and I compete against the incumbent generation owners, and I can do so because I've hedged my wholesale price risk from this purchase in this futures market. Then the other is, did this introduction of these standardized markets lead to lower wholesale prices? Here the logic is, I introduced these purely financial retailers. They had an increased demand for these hedges from the forward market. In the counterparty to most of these hedges would be physical players. These physical players would now have more fixed price forward contract commitments coming into real time. They would therefore bid more aggressively in the short-term market as a result of these larger commitments into the short-term market. For those of you who would like to know more about that, a paper on my website talks about those incentives. And so what did we find? Well, what we found in this paper was that effectively the competition from the purely financial retailers led to about a 10 to 15% lower average retail contract price over about 10,000 contracts that the Singaporean regulator had collected and made available to me over pre versus post this intervention. And then again, the increased fixed price forward contracting of these purely financial retailers led to about 5 to 10% lower wholesale prices during the delivery period of these contracts. So the benefits in terms of this, but more importantly, the having and welcoming purely financial participants into your market reduces the barriers to entry into electricity retailing. What do? I essentially buy this financial contract. I then compete against incumbent generation owning retailers to sell energy against them. I get enough customers. Then eventually what I do is I decide, gee, I've got enough retail customers. I can then use that to essentially finance a electricity generation unit, lower the barriers to entry to getting new generation into the market, and therefore improve both the competitiveness of retail and wholesale market. So the other thing that purely financial participants can do, or these purely financial retailers, is they can sell financially binding load reductions. And this essentially just works is, if I buy 100 in the day ahead and I get my customers not to consume it, then essentially say they consume 90 instead, and the real-time price is 80, I'm effectively pocketing 80 minus 30 for that 10 megawatt hours. And the nice thing about this multi-settlement locational pricing market is it avoids the need for demand reductions to essentially be paid according to, say, an administratively determined baseline. You basically buy energy day ahead and you sell it in real time, rather than you play what happens in many markets around the world that don't have a two-settlement, multi-settlement LMP market, is you essentially play the game of give me a very high administrative baseline relative to which I get paid for demand reductions. And this creates reliability problems for the system operator, because they really don't know how much demand reductions actually supplied if you're measuring it relative to this administrative baseline. It is largely eliminated. And so there are opportunities in many of these markets for these purely financial retailers to get in there as well. And one of the interesting things, based on some work we've done in Denmark, is the fact that you can even have paid people into the new regime. You pay them to consume more during certain periods of high renewables output. And this has the potential, and we give some examples in the paper, that it can increase the profits of the retailer, reduce the bills of customers because they receive the rebate, and even reduce greenhouse gas emissions in the region. Why? Because what you're doing is the mechanism, as I state, is that you're shifting consumption from the high price periods when fossil fuel units are producing, reducing greenhouse gas emissions, into regions, into time periods where excess renewable energy that would be, say, curtailed or exported outside the region, say, is producing. And so there you're getting the greenhouse gas emissions reduction, and you're essentially getting a small, maybe positive or negative net energy change for the day for the customer. Consume more in the low price period, consume less in the high price periods. And so you're getting effectively a net winner. So these sorts of, one of the things that financial participants can do is create and come up with these creative ways to essentially help customers become flexible in the short-term market. Because their incentive is not to sell more electricity. Their incentive is to provide a value-added service to the customer and essentially share in the benefits of that value-added service that they provide. So the next thing is cross-hedging. And here, one of the big issues with respect to renewables and thermal resources is this idea of the fact that the standardized product that we typically historically sold in all of these markets was a fixed price forward contract. And so the idea would be is I essentially sell you QC megawatt hours at some future delivery date at price PC, and essentially the profit that they receive of this action is essentially the difference between the contract price minus the spot price times QC. That's essentially the difference payment that I get, or I have to pay as the generator that sells this. The, say, retailer that buys this, they get the other direction of this difference payment. And so, you know, these contracts effectively just become, as we say, bets on the short-term price. If the short-term price is above the contract price, the payment goes from the purchaser of the contract from the generator. If the short-term price is below the contract price, this area, the gray area payment right here, goes to the purchaser, typically the retailer, from the seller of the hedge contract. It essentially gives price certainty to both parties for QC units of energy. If QC energy units are consumed or QC energy units are produced, the producer gets price certainty at PC, the consumer gets price certainty of PC for that. But this also has implications for their behavior. There are other kinds of contracts that get traded and sold. There include cap contracts, where essentially the owner essentially gets paid the difference between the short-term price and the strike price if that difference is positive. So that's the max of zero in that times QC. There's also what are called put options, which is just switching the difference, meaning it gets paid the max of the difference between the strike price and the price P. And then there are more exotic forms of these contracts that can happen. But the way cross-hedging can work is if, and this is something that definitely needs to be implemented and is being slowly, hopefully implemented in most of the US markets, is that intermittent renewable resource owners sell the same products as dispatchable thermal resource owners, meaning they sell fixed price, fixed quantity contracts, not fixed price whenever I want to produce contracts. That is an implicit subsidy to renewable resource owners that essentially is not viable in a world in which most of your energy is coming from those resource owners. They have no incentive to manage their quantity risk, no incentive to manage short-term price risk. They're completely out of the short-term market. So, but if what we do is we require them to sell products that dispatchable thermal resource owners sell, meaning fixed price, fixed quantity contracts, or pre-specified pattern of output quantity contracts, then essentially there will be a demand for cross-hedging. In other words, the intermittent resource that sells this contract will want to reinsure the risks that it faces. So in particular, if, as I showed here, that it produces nothing within the hour, but it sold forward something in the hour, it's on the hook if that price spike occurs, and it's got to pay the difference between P and P minus PC times the amount of energy that it sold. This is precisely what happened to a number of wind resource owners in the ERCOT market that sold what are called bank forward contracts, which were essentially these purely financial contracts, and they were on the hook for the huge price spikes that existed during the period because they did not provide the amount of energy that they contracted for. Whereas, so what can happen is the dispatchable thermal resource has additional challenge because of this increase in the amount of intermittent renewables. That is, that it produces output many fewer hours in the year and has fewer opportunities to recover its fixed costs. So a match made in heaven is the sale of a cap contract between the intermittent resource that has to participate on equal footing with any other resource and sell the product that consumers want, which is a hedge against a known price quantity pattern or fixed quantity. And it then purchases this cap contract, and what it does is pays an upfront insurance cost, and in exchange, it gets this payment stream right here if it fails to produce any output. It basically loses the difference payment as we talked about because of the price spiking, but because it purchased this this cap contract, its sort of downside is limited, and meaning that the payment stream, if suppose what it did is it purchased the same quantity in the cap contract that it has in the swap contract, it only loses PC minus PCS times QC, and it gets essentially, it takes on significantly less risk. And then on the other hand, the thermal resource now has this fixed payment that can go to fixed cost recovery. And moreover, it has a very strong incentive to make sure that the short-term price never does go above the strike price of this cap contract, because otherwise it has to make this payment that goes to the intermittent resource. So we get this nice cross-hedging that takes place between the intermittent quantity risk of the resource and the dispatchable thermal resource, one of which helps to keep the dispatchable thermal resource that operates less frequently in the market, the other which requires the intermittent resource to pay for the cost of its intermittency rather than push that on to the market, as is the case if it sold a fixed price variable quantity contract. So the other thing about purely financial players is this provision of liquidity. A complaint that you hear in virtually all markets is this lack of liquidity in the forward market for long enough horizons into the future to finance new investments. And purely financial participants, if you get them into the market, can help to provide this liquidity. They get this familiarity with how the short-term market operates. They can then take the, if you like, sort of the back-end revenue stream for a potential new entrant that, say, a retailer might not want to take because of the fact that it doesn't know what its load might be. And then what the financial player can do is sell the energy to the retailer as delivery date comes closer to the retailers that actually need the energy. And clearly, this is a risk they're taking on, and they should earn a return for this. But this is, I think, a very important role as well for financial players in the market. And then the last point is the fact that, well, if we've got these risk managers in there, these purely financial players that understand and can increase flexibility, can get these plants online, do we really need this sort of backward-looking resource adequacy requirement that essentially says you got to have enough capacity to meet the 1 in 10 outage standard? Maybe we can get by with essentially a smaller capacity requirement that could really harvest, again, significant benefits to consumers, because we have to pay for and bring online fewer generation units in order to keep the lights on and maintain a given level of reliability. So financial players have a significant role to play there. All right, so to finish up is, you know, if just restating things, the financial players, I think, can really step in and provide significant benefits if the short-term market is properly defined. These are ways that they can do that. And I think that their role and what they can provide is going to be even greater as we scale up the amount of intermittent renewables that we have. The demand for risk management services, sophisticated out-of-the-box thinking in terms of how to manage that risk is going to become even greater. And so it to me seems behoove to figure out ways to get them involved in the short-term market. So thank you very much. I'll stop here.